slopes of lines, and rates of change. The objective of this lesson is to numerically describe and interpret the slope of a line. Okay. So slope. The slope of a line is the slope of a line is the measure of its steepness and direction. So we can tell how steep a line is and what direction the line goes. So first we're going to talk about this direction component. We read graphs much in the same way that we read words, left to right. So we read graphs from left to right. So just like we would read this as positive slope, we read the P first, the O left to right. We're going to read graphs also from left to right. And so if my line goes up from left to right, like that, or like that, or like this, all of these lines go up as I read it from left to right. And I always start with, if I'm thinking of a little guy on my line here, starting on the left-hand side, which way is he walking as he walks to the right? He's walking up. So if a line has a positive slope, it's walking up. The line goes up. So negative slope goes down from left to right. Go like that, like that. It could be really steep down, but negative slope goes down from left to right. Okay, so let's go ahead and let's practice identifying lines with positive slope and negative slope. So which lines over here on the right have positive slope? Which have negative slope? So I'm going to go ahead and I'm going to list my positive slope. So which ones go up from left to right? The first one I see is this line 4. Line 4 goes up from left to right. So positive slope would be line 4. Okay, and let's go ahead, let's create a negative slope list. Okay, so let's go ahead, let's look at line 4 to me was the obvious, go up. Let's go ahead, let's look at line 1 here in blue. Line 1 there is blue. Again, we read from left to right, so if there's a little man on here, he's going to be walking down. So line 1 has a negative slope. Okay, so we got line 1. Line 2, right there in green. Oh, right there in green's line 2. Is that down or is that up? Again, think of a little man on the far left side. He would be going down, very steeply down, but he'd be going down. So line 2 also has a negative slope. Line 3, this red guy right here. Okay, again, farthest left side would be right here. Think of that little man. Which way would he be walking? He's walking up, really steep up. So line 3 has a positive slope. So we have 2 with a positive slope, 3 and 4, the purple and the red, and then 2 with a negative slope, line 1 and 2. Of the 2 lines with positive slope, so just looking at line 3 and line 4, which one rises more steeply? That is, which line is more vertical? Or which one would be harder to climb? If I had a little man on this one, my little stick guys, and I had a little man on this one, which one is a harder climb? Line 3. Line 3 is steeper. Okay. Line 3 is steeper. It's just, it goes up faster than the other one does. Okay, of the 2 lines for part C, of the 2 lines with negative slope, looking at line 1 and line 2, which one falls more steeply? That is, which line is more vertical? So again, think of a little guy on line 1, a little guy on line 2. Line 2, he's darn near falling almost straight down. Not quite, but almost. So line 2 is steeper. Okay, when it comes to our negative slope lines. Okay, now we're going to start giving some numerical values. Slope is not only direction, positive or negative, but it's also steepness. Line 4 has a slope of 1/2. Sorry, and line 1 has a slope of -1. Of these 2 lines, which is steeper? How can you tell from the given slopes? So if we look at line 4, again, we're just looking at line 4. Line 4 is this guy right here. It's got a slope of 1/2. line 1 has a slope of -1. Which one is steeper? So again, think about which one's going to be a harder climb, this guy here or this guy here. Okay, which one is going to be a steeper climb? Line 1 here has a much steeper climb than this one. This is a nice gradual slope up. This one gets quite a bit steeper. So line 1 is steeper. And if you look at the slope values, 1/2 compared to 1, 1 is greater than 1/2. So it's steeper. Again, I ignored that negative. That negative tells me the direction that it's going down. The negative tells me that the line is going down. The 1 tells me how steep it is. This 1/2 here is positive, gives me the direction. The 1/2 tells how steep it is. Line 1 is steeper because a slope of 1 is greater than a slope of 1/2. Okay. So now how do we find, here we talked in this part D, we talked about giving numerical values to slope. How do we find that slope? One way is you can find slope from the graph. So here I have two different lines. I have a blue line. We'll go ahead, call that blue line line 1. And then I have a red line here. We'll call that red line line 2. Okay. To find the slope, a slope again is that measure of steepness. So for line 1, okay, that steepness, how we used to measure it is how far up and down. How far up and down does it take to go over so far up and down? Because if I can go up faster than I can over, that's going to be steeper than up a little bit and over a lot. Okay, so to determine slope from a graph, we take the ratio of the rise of the graph, how fast does it go up and down, over the run of the graph. How far does it go left and right? So to be able to determine that, for line 1, to find its slope, I find two nice points on this graph. Well, this right here is a nice point. It's the 0.55. And I look how far and then find another nice point. That's kind of an in-between. Oh, this one right here is nice. So there's my two nice points. And I look for how far do I go to get from one point to the other? Now this one, my rise here is I go down 5. So down's negative. Whenever you go down, it's negative. I go down 5. So my rise is down 5. My run, how far over do I go? Again, make sure you look at your scale here. I'm counting by 5s. I go over 5, 10. I go over 10. So I go down 5 over 10. I know as I read this line, it should go down. So I know the slope needs to be negative. So I have -5 over 10, which gives me a slope, if I simplify that, -1/2. The slope of that line is -1/2, -5 over 10. That's the slope of that line no matter what points I pick. Okay, I went rise, down, run over 10. Now, if I would have did it the other way around, so that was me going down first and then over. Let's say I did it the other way around. Sorry, let me just erase. Oh, that's not erasing. Let's erase this stuff. And instead, let's say I went the other way around. Let's say I started here at 15 and I went over here to 5. Well, to get from, if I'm going from 15 over here to 5, I go up first. So I would go up 5. So that'd be positive. But then I go to the left, which is -10. So then I would have 5 over -10, which guess what? That still simplifies to -1/2. Okay, so when you go to the left, it's negative, and when you go down, it's to the negative, which is just how our number lines work. That's nothing new. So the slope of that blue line is -1/2. Now let's compare it to the slope of the red line, line 2. Okay, so again, we find two nice points. This right here is a nice point, 0.0 up 5. Oh, and this one here is pretty nice too. So to get from here, my rise, I go up 5. Rise is 5. My run, I go over also 5. And 5 over 5 is 1. Okay, let's say hypothetically I didn't pick those 2 points. Let's say I picked this one and this one up here. Again, rise there, I go up 10. I go over 10, and 10 over 10 is also 1. Okay, all right, hypothetically, let's say I go the other way. Let's say I pick this one, but I go backwards, back 10, and then down 10, negative 10. Well, I'd end up with negative 10 over negative 10, which lo and behold is also 1. The slope is always 1, no matter which points you pick, as long as you pick exact points on the line. The slope for this red one is always 1. Okay, so there's so many different ways of getting that slope, as long as you're consistent with that rise over run idea. Okay. Sorry. Slope is rise over run. There's our important information, our rise over run. Okay. All right, slope transfers in really good to what we call as a rate of change, because slope is a ratio. This is the ratio of rise to run. A ratio is really just any division of two numbers, if you remember. A ratio is just a division of two numbers, so a ratio or division. So a rate of change is the ratio of the amount of change in the dependent variable to the amount of change in the independent. Okay, now the dependent variable most of the time is our y, because it depends on what x is. A dependent depends on someone else, whereas the independent is our x. He doesn't depend on anybody. He is independent. I can put in whatever I want for the x. Okay, and then I depends on what the equation is on what I get for my y. Hence my y is my dependent. It depends on the x. That's why we do our ordered pairs x then y. I need to do my x first, figure out what that is, because that determines what my y is going to be. Okay. Okay, so it's the rate of change, the ratio of the amount of change in the dependent. Well, if my dependent is my y is your up and down. Again, remember, y is up and down on a graph. Like your y-axis. Your y-axis is the up and down, the x-axis is the left and right. So it's the ratio, the division of the y, which is the up and down. Well, isn't that just the rise from up here? Our rise was our how far up, how far down. Okay. Over the ratio of the dependent to the independent, which is our x, which is that left and right. Well, isn't that just our run? So do you see how the rate of change is really just slope? Rate of change, I like to say, is slope with context. Okay. What I mean by that is up here, these lines that we were doing up here didn't represent anything. It wasn't talking about gas mileage. It wasn't talking about amount of money. It had no context. We had no idea what this line represented. It didn't represent anything. It was just a bare bones number problem. Hey, now if I give it context, meaning if I give it an application, if we're talking about money, or we're talking about time, or number of tables, or amount of food, if it's given context and I find the slope, that's just rate of change. Okay. So, like in this problem, here we have a car traveling at a constant speed. So the speed doesn't ever change. That speed is constant. Okay, and we know that if I've traveled 45 miles, I have 12 gallons of gas left. After 255 miles, I have 5 gallons of gas left. Okay, so really, if we put a graph to this, if my distance traveled is my x, or in this case, they use d, this would be my independent. Because the gasoline I have left depends on how far I travel. So my dependent is my gasoline left, because it depends on how far I travel. The amount of gas I have left in my tank is dependent on how much I travel. So here, so this is my point, my 45 after 45 miles. So again, this is my miles, 45 miles, I have 12 gallons of gas, or they use distance. D is my distance. I have 12 gallons of gas left. Here, after 225 miles is my distance, I have 5 gallons of gas left. And then we connected those points with a line, so we can see this nice little linear relationship. Okay. So we want to determine the rise between these 2 points. So we want to determine the rise. Well, first of all, it's not a rise. Well, it is a rise, but it goes down. To get from this point to this point, it goes down. It's a lot harder to count because it's like a partial, but I can look at how high is this point here. It's up here at 12. How high is this point here? It's down here at 5 because we're looking at those y values. So the rise is again looking at the y values. Okay, so here I'm going from 12 to 5. So the difference between the two, 12 minus 5, would give me 7. What does the rise represent? Well, that represents 7. Well, and it's actually down 7. So I would actually probably want to subtract that the other way. 5 minus 12, because I'm going down, it's going down 7. What does the rise represent? Rise is gasoline left. So gasoline left. So basically, the -7 tells me that I went down 7 gallons of gas. Okay, so over this time, I went down 7 gallons of gas. What units are associated with the rise? Well, I just said gallons. What units? Gallons. Okay, so I went down 7 gallons of gas. Okay, so now it asks, what is the run? Determine the run between the 2 points. So I'm looking how far over. What's my run right here? Well, here I'm at 45, and I go over to 255. Okay, so how far do I go over? To go from 45 to 255? Well, I would need to take 255 minus 45, which gives me 210. My run is 210. What does the run represent? Well, let's look at its distance traveled. It means I traveled 210 miles. What units? The units are miles. We traveled 210 miles. Now find the slope. We know slope is rise over run. Sorry, let's switch colors. We know slope is rise over run. So my rise is -7. My run is 210 miles. I'm going to put units on this. So if we simplify that, -7 goes into 210 30 times -1 over 30 is my slope. What units are associated with the slope? Well, that's why I wrote the units in. Gallons and miles. First of all, what does the slope represent? I lose. So here, this is gallons. Again, miles. So this tells me I go down 1 gallon every 30 miles. Or I go down 1/30 gallons per mile. What units are associated with the slope? Gallons per mile. That is the rate of change here. So this tells me for every 30 miles over I go down 1 gallon. I go down 1 gallon for every 30 miles. Okay. Or down 1/30 a gallon. So every mile I drive, I'm losing 1/30 of a gallon. Okay. That is that rate of change. Okay. So I go down 1/30 of a gallon per mile. Okay. So what if I don't have a graph or I don't want to graph it and I want to find the slope? That's another way to find the slope. So another way to find the slope is using ordered pairs. Okay. So here I have a graph with 2 points. I want to find the slope between these 2 points. Okay. I want to find the slope between this point and this point, but I have no scale. Okay. So it's really hard to just count. Like I would want to count rise would be up. There's my rise. And then my run will be my over to find the slope between these 2 points. So how do I find it? Okay, all I really need to know is the x and y coordinate for each of these points. Let's go ahead and let's mark this thing up. So this point down here is going to have coordinates x and y. And this point up here is going to have coordinates x and y. Okay, but I can't just use x and y because then I don't know which one I'm talking about. So what we're going to do is we're going to introduce what's called a subscript. I'm going to put little bitty, let me make this a little bit larger down here. Sorry, it's not wanting to erase very good. I'm going to make this a little bit larger. We use little bitty subscripts. I'm going to have this be my first point. And we say that's x sub 1 and y sub 1. And then I'm going to call this point 2. X sub 2 and y sub 2. It does not matter which is which. It does not matter. I could have made this one 2, this one 1, could have made this one 2. Doesn't matter. We just put the little points on it to basically tell them apart. Okay. So the rise is how far do I go from this y up to this y? How far is that distance? Well, this here is my y1. This one up here is my y2. So basically I'm looking for what is that distance? Well, to find the distance between 2 points, let's go ahead, let's write rise over run. I just need to figure out how far apart are they. So basically I subtract the 2. Normally we take the bigger one minus the smaller one. Okay, so because in this case, this one's the top one, but it really doesn't matter which way you subtract. So I'm just subtracting this y coordinate from this y coordinate, and that is my rise. Okay, now my run, this would be x sub 1. This would be x sub 2. So now my run is this distance from here to here. So again, same difference. We're taking those x values and subtracting them. X sub 2 minus x sub 1. The only thing that matters, it does not matter which order you subtract here. The only thing that matters is these 2 make an ordered pair and these 2 make an ordered pair. That you don't flip-flop halfway through the problem. If I pick this y first, I have to use this x first. This y first, this x first. If I did it the other way around, that would be completely okay. I shortcut this by using this symbol, which is the symbol, it's a Greek letter delta. It means change. I want to know the change in the y over the change in the x, meaning what's the change from here to here. And we get that by subtracting. So all of these mean the same thing. Okay, it's just will save you from having to count the rise and run. You can just subtract to find the rise and run. Okay, for example here, I want to find slope, which instead of using the word slope all the time, we use the letter M. Slope is M. Do not ask me why they use M for slope. There's a bunch of different conflicting reasons around there, but for slope, we use the letter M. Okay, so here M, slope, is equal to rise over run, or I like change in y over change in x. So I just need to first identify, for change in y, identify my y coordinates, 5 and negative 6. So I subtract them, 5 minus a negative 6 over, now I identify my x coordinates, 4 and negative 3. Since I used this 5 first, I have to use the 4 first. So we'll go 4 minus a negative 3. Okay, now if you have a hard time subtracting negatives, you can totally use a calculator to do this top part. But 5 minus a negative 6 is the same as 5 plus the opposite of 6, which is 6. 4 minus a negative 3 is the same as 4 plus the opposite of negative 3 is 3. So my slope ends up being 11 over 7. Okay, and then I always look to see, is it the right, this line goes up, so I should have a positive slope. Oh. I always look to see, do I have a positive slope? I do. 11 over 7, and we just leave it as a fraction in simplest form. We like slope as fractions. Slope as fractions is nice. Okay, now if I would have did it the other way around, okay, so now I'm going to go ahead and I'm going to go do it the other way around. So let's say I would have did the negative 6 first. Negative 6 minus 5 over negative 3 minus 4. So it would have been negative 6 plus a negative 5 over negative 3 plus a negative 4, which gives me negative 11 over negative 7, which a negative divided by a negative is positive 11 over 7. Same answer, okay, if I would have flip-flopped them around. So it doesn't matter which order in which you subtract. Okay, next one. A line with slope 3/5. So I'm going to write slope is 3/5. Rise over run. Passes through the point negative 1, 1. Determine another point on the line. First, I'm going to start by putting this point on my line over here. So it goes to the point negative 1, 1. There's my point. I know it has to have a slope of 3/5. So I need to have, it has a rise of 3. So from here, I'm going to go up 1, 2, 3, and then a run of 5. 1, 2, 3, 4, 5. So there's another point on the line, the point 4, 2. Okay, I can keep going. Again, slope of 1, 2, 3, rise of 3, run of 1, 2, 3, 4, 5. There's another point on the line, 9, 5. I could also go backwards, okay, and treat it as negative 3 over negative 5. So from this point, I could go down 1, 2, 3, back 1, 2, 3, 5. There's another point, negative 6, negative 4. All of these are points on the line, because if you look, if I connect all my dots here, all makes one nice line. Okay, so we use that slope. All right, now let's do some problem solving. Here we have Tracy. Tracy runs every Saturday to stay healthy. After stretching, he always begins by jogging at a steady pace. He uses a fitness watch to monitor both his time running and his pace. At the end of his jog, he immediately increases his pace to a regular running speed for the remainder of his workout. Find the average rate of change, or that average speed, for his entire workout. So the graph models his time and distance run during the workout. So if you notice, so here's time, here's distance ran. So here, from here to here, if you notice, it has one steepness. So that's his jog. And then from here to here has a different steepness. So I'm assuming that is his running. We want to determine the rate of change for the 10 minutes while he is jogging. So we want to find the slope for this first chunk right here. So I think I'm going to count my rise. First of all, the slope is positive. That's always good to identify first. So once you find it, you know whether you're right. Okay, my rise, I go up. Be careful here. My units are, that goes up a half. My rise over run. My rise is 1/2 over my run is, these are counting by 5s, 5, 10, over 10. So 1/2 over 10. That rise is distance ran. So 1/2 a mile, 1/2 miles. Per my run is time in minutes. So what are the units for this rate of change? I found it, miles per minute. Hey, now 1/2 over 10, we don't really like that, so I'm going to go to a calculator. Actually, let's just use, sure. We'll use Desmos. 1/2, oh, that's not 1/2. 1/2, and then we want to take that divided by 10 is 0.05, which is 1 over 20th, 1 over 20, 0.05 miles per minute, or I like 1 over 20. So basically he goes 1 mile every 20 minutes. He can do a mile in 20 minutes is what that's telling us at that jogging speed. So determine the rate of change for the 10 minutes while he is jogging. He can go 0.05 miles per minute or 1 mile per 20 minutes. And what are the units? Miles per minute. That's while he's jogging. Determine the rate of change for the 40 minutes while he is running. How does this rate compare to the rate of his while jogging? So again here, so now we're going to calculate it for here while he's running. So from here to here. So now we're going to calculate it for this distance right here, for that part of the graph. Okay. We can do rise and run right here, or we can go ahead and let's do, so this is the point 10 up a half, and this is the point 50 up 5.5, 5.5. Okay, so we could do rise. So to find the slope for that, I'm going to do change in y over change in x. Just because I don't want to count all that. Okay, my change in y, we're up 5.5 minus 1/2. So there's my change in y, and then we have our 50 minus the 10. 5.5 minus half is just 5. 50 minus 10 is 40. So 5 over 40, which 5 goes into 40 8 times, 1/8. Again, miles per minute, which if we want a decimal for that, 1/8 is 0.125 miles per minute. Or you can go 1 mile in 8 minutes as opposed to his 1 mile in 20 minutes while jogging. Okay, so how does this rate compare to the rate while jogging? His running rate is more. Running rate is more than jogging rate, right? Because he goes 1 mile in 8 minutes as opposed to 1 mile in 20 minutes. Now determine the average rate of change for his entire workout. So basically we're going to ignore the speed change and just go from beginning to end. So here, just beginning, which is at the point 0, 0, to the end, which is the point 50, 5.5. Okay, so we want to find the rate of change for that. Again, change in y over change in x. Okay, well, let's not do, so my change in y, we're going from 5.5 to 0. So 5.5 minus 0. And then 50 minus 0 for the change in x. So I'd have 5.5 over 50, which would be 5.5, 5.5 over 50, 0.11, or 11 over 100, 0.11 miles per minute, or 1 over 11 over 100 miles. You can go 11 miles in 100 minutes. In this case, I think I like this version better. 0.11 miles per minute, as opposed to his 0.125 miles per minute, as opposed to his 0.05 miles per minute. So if you notice, his jogging was 0.05, which is less than the 0.11. And his running was 0.125, which is more than the 0.11. So over the entire, which makes sense, that over the entire bit, that this bit of jogging made his rate of change over the entire trip less than it would be if he just ran the whole entire thing. Okay, so explain why this makes sense for this real world situation. Well, since rate was slower while jogging, his average rate is less than his running rate. Since he has that little bit, it's not less by a lot, like 0.11, 0.125, not a whole lot, but it is less by a little because of this slow part of his run. Okay, so there we are calculating rate of change.